calculates the overall collection efficiency of a particle control device. Okay? Okay, because we know different particles sizes have different collection efficiency. Okay? Different particle sizes. Different particle sizes have different collection efficiency. 收集效率 Okay? Different particle sizes have different collection efficiency. Okay, therefore we need to find out the overall efficiency. Okay, so this is the formula. So this is formula. Okay, so this is formula. So eta. Okay, this Greek alphabet pronounced as eta. So eta over O equal sum. Okay, sigmas. Sum of eta j times mj. So eta j stands for collection efficiency for J size, which means the collection efficiency for particle size include J. Okay, J size J's means include J. And MJ stands for the mass percentage or mass fractions in the size group J. Okay, so let's do these questions. So first of all, if we have this. Okay, we have the size smaller than 1. Okay, and this occupies 1%. Okay. So this is particle size. The first one, dp, this is particle size. And this is average size. And this is mass percentage. And this is collection efficiency. Okay, so less than 1%. 1 to 3, 9%. Okay. So how to calculate this? How to calculate this? Okay, very simple. Okay. So So the data we need, based on the formula, okay, the data we need is the mass percentage and eta J. Okay, so this guy actually is MJ. Okay, this is MJ. This guy actually is MJ. So MJ times A dot J, right? So 1% times 9% plus 9% times 55. That's it. Super easy. Sum of this. Okay, then you've got 87%. Let's write this one down. Okay, so the overall efficiency, okay, this guy times this guy, and add them up, and add them up. Okay? So next I would like to talk about absorption band. So absorption band is an air pollution control device. Okay. So it's good for removing gas phase pollutions. Okay. It's good for removing gas phase. So it's good for removing gas phase pollutant. From the air or any gas stream. Okay? So as we know, absorption actually is surface phenomenon. Okay, so this means the pollutant particle will not enter, will not go deep inside. Okay, so last time I already told you, right? At adsorption is not equal absorption. These two words are different. These two words are different. So absorption, one is adsorption, the other is absorption. So absorption is a surface phenomenon. That means the pollutant molecules do not go deep inside. Okay? So they will just attach to. They just attach to the surface. Okay, or stick on the surface. For example, like the reason we use adiabatic carbon, right? Those pollutant molecules will stick to the surface of adiabatic carbon. Alright? And it evolved physical or chemical bonds with surface. Okay? So one is a physical absorption, but this is very weak. It's very weak for something like van der Waals force. Okay? And the other is chemical bond. Physical or chemical bonding. Okay, and what kind of absorbance? What kind of absorbent we can use? Okay, first and the most commonly used is activated carbon. Okay, most commonly used is activated carbon. Okay, and we can also use activated aluminum. Activated aluminum is good for removing, for example, like mixture, some gases, some special gases, and moisture. Okay, some special gases and moisture. And also we can use something like silicas and others for special purpose. Okay, some acidic gases or some polar gases. Some polar gases or some acidic gases and moisture. Silica gel, okay, silica gel and others. Okay, so silica gel normally is good for the moisture as well. Okay, good for moisture. Water. Okay, the reason the activated carbon is most commonly used is you can imagine this. 1 ounce of activated carbons has a surface area of 5 to 10 acres. So the surface is huge. The surface area is huge for activated carbon. And keep this one in mind, those absorption back must be regenerated. Okay, regenerated, must be regenerated or renewed prior to breakthrough. Understand? Okay, everyone okay? Okay, so this is typical absorption bed look like, but in industrial you can see it's not a tiny one, it's huge. You can see that. This is industrial scale, 工业级的, it's huge. Okay, so this is for the dirty air gas inlet, right? And you have a carbon back here, and you collect the clean gas or clean air outlet here. All right? Okay? So next, I would like to introduce electrostatic precipitate. Okay, sometimes we call this, student, back here, ESP. So ESP stands for electrostatic precipitator. Okay, and we have two configurations of ESP. One is wire in tube. The other one is wire and plate. So this one, student, the figure 9-42. On the left hand side, the figure A is wire in tube. Okay, so this guy is wire in tube. Okay, on the right hand side, you can see the plate here, right? So this guy is called wire and plate. So there are two configurations, okay, of ESP. So one is called wire in tube. Okay, one is called wire in tube. The other one is called wire and plate. Wire and plate. Okay, so ESP is good for removing. So ESP is good for removing solid particles from the gas stream. Write this one down. So ESP is good for removing solid particles from the gas stream. Okay? Finish? Everyone? Okay, so wet or dry. Okay, so ESP can handle wet or dry. Okay, wet or dry. Okay. So, let me write down here. So dry ESP. Okay, ESP can be cleaned in two ways. Wet or dry. Wet or dry. Okay, for the dry ESP, the dust is removed by something called ripping. The dry ESP, the dust is removed by something called wrapping. Okay, what does wrapping mean? Wrapping means shaking. Just shaking. Okay, or heating the collecting plates. Okay, for wet ESP, as I mentioned here, right? The plates are cleaned by water Doing okay? So there are two kinds of cleaning. Dry cleaning, okay? Dry ESP or wet ESP. For dry ESP, the dust must be removed by wrapping. Okay, wrapping means checking. Or just heating. The wet ESP, for the wet ESP, the plates are cleaned by water spray. Okay, next I would like to introduce Corona. Corona wire. Okay, not coronavirus. Okay, also not the beer, Corona beer. It's Corona wire. Okay, Corona wire, what is that? The Corona wire is high voltage. High voltage wire inside the ESP. Okay? So the electric fields ionize the gas. So they try to ionize. Okay, they apply electric field and try to ionize the gas particle. Ionize the gas around the wire. Okay, in this case, you can get charged particle. You provide charged particle. Charged particles. And high pressure will be applied. High pressure will be applied to increase the removal efficiency. So let's see these figures. Student, let's review. So the gas flow, right? And this is uncharged particles, right? So we apply the electric field here. This electric field try to ionize the gas around the corona wire. Okay, and those gas become charged particles. Okay, and those charged particles, so put charge here. Those charged particles were attracted to the collector electrodes and form the dust layer. Okay, the clean air, the clean gas can be collected here. Okay, I would like to raise the questions. Why ESP? I'm going to ask this kind of question in the exam. Why ESP has dry removal efficiency. Because it's ESP uses strong electrical field, right? Electric field. Instead of mechanical filtration. So it applies electric field. So efficiency is better. So after that you need to clean. Okay. After that you need to clean. Before you need to clean, after your collection, you also need to clean. Before collection you need to clean. After collection you also need to clean. Okay. Depends on dry ESP or wet ESP. By wrapping or by the water spray. Okay. This slide just tell you what is wire do, what is wire and plates. And this one show you the working principle for ESP, right? Okay, so those charge particles will be attracted to the electrode. Okay, let's do these questions. Okay, this question, first of all, let's see the formula. So this is the ESP equation. So eta equals 1 minus exponentials minus AW over QG. Okay, so A is collection area. Okay, W is the migration velocity, and QG is the gas flow rate. Student, I got this equation from our tester. Okay, so again and again, you need to read the tester. All right. Okay, so this one the eta. So this is how you calculate the ESP efficiency. Okay? And also based on the formula, you will know the higher the A, higher the correction area, the better the efficiency, right? The higher the vibration, the higher the vibrations velocity. And also, however, higher the QG, the eta will be lower. Higher QG, the beta will be lower. Okay, sometimes the question will not give you migration velocity, so you need to calculate by yourself. Okay, so this is the formula that we calculate migration velocity. Okay, student, let's do this question. So this is the plate and wire question, right? Let's see what we have here. So the question asks us to determine the collection efficiency eta. Okay, so they give us height, they give us length, they give us the number of plate 5, plate spacings. Okay, plate spacing 间距. So plate spacing is 0.28 meters, right? Gas flow rates 19.73. But we don't have W here. We don't have a drift. We don't have drift velocity. But the question gives us. So W is 0. That's China just attack us. Because Trump is there, you know. Okay. So it's 0.184 MOS. Okay, student, I want you to do this question before we take a short break, okay? Okay, student, this is the question. This is the question I will ask. This is some kind of similar question I will ask in the exam, okay? I probably will give 8 questions. Probably, I don't know. 4 calculation question, 4 essay question, and 20% for multiple choice. Okay?不给你们解答吗？这个没有，这样会属于 OK. Let's save some time, okay? But this is from test 3. You can take a photo or you can see your test 3. Okay, let's do it. First off, okay? And also, I will not ask you to derive the equation. 我不会叫你推导公式. I will not ask you to derive the equation. So, what you need to know is, you need to know how to use those equations. So what do we mean? What do we need? So what is missing? Area, right? Students, take a look. The equation 9-69. We don't have area here. Right? We don't have area. So, step 1, we need to find the area. Okay, we need to find the area here. Yeah. Step 1, we need to find area. Okay, for a single plate. So the area is 44.65. Okay, and why we time 8? Okay, because student, we have 5 plate, right? But 1, 2, 3, 7, 4, 5, 6, 7, 8. So this doesn't count. This doesn't count. Understand? Student, understand? So only the inside area count, right? So 1, 2, 3, 4, 5, 6, 8. So that's the reason we need to time 8. Because 5 plates, but we have 4 passage. Okay? 5 plate, we have 4 passage. So times 8. So the total area is 357.2. Okay? So put this in. And we have the rest of it is not. Then we find out the efficiency. So this is the efficiency. So it's reading height 96.4%. Okay, second question, if we reduce. Okay, second question, if the effect of reducing, so this is number 1, this is answer for The first question. Second question, the effect of reducing plate spacing. Okay, so that means was 0.28, right? I want to reduce to half. I want to reduce this to 0.14. Sorry. The 空隙要减半 okay? So reduce 0.28 to 0.14. Reduce half. Okay? So the W equals KEP and 0, this is was. Okay, that was original, and this is new. We want to reduce from 0.28 to 0.14. So this becomes 2 KEP. So 2 KEP means the area needs times 2. So 3357.2 times 2. So area times 2. But the rest of it remains the same. As you can see, if you reduce the spacing, the efficiency raised from 96.4% to 99.9%, even close to 100%. Okay? So spacing matter. If you reduce, in this case, right? You reduce the spacing. Okay, you reduce the spacing from reduce spacing half to halfway, right? 0.28 to 0.14. Then efficiency. The efficiency increase from 96 to close to 100. Okay, this is reasonable. Why? Let me finish this before we take a short break. This is reasonable. Why? Because smaller spacing decrease, right? You decrease the spacing, you have the electric field. Increase, right? So you reduce the spacing, you increase the electric field, and also because you increase the electric field, you increase the migration velocity. Okay? Understand? So you increase you decrease the spacing, you increase the electric field. And also, because you increase the electric field, you increase the migration velocity. Okay, let's write this one down. But this is the advantage. But how about the disadvantage? Okay, the disadvantage, for example, like because the smaller spacing means you must operate careful because your electric field increase, right? Okay, and it increase, the higher risk of blockage. And also difficult because the spacing is too small, so it's difficult to clean. Okay, we know based on calculation, based on theory, we know the smaller spacing is better, but there are still some limitations. So you need to find out the optimal spacing for your ESP. Okay? Okay, let's have a short break.